So in this video, we get to state our first asymptotics result about the coefficients of generating functions. So here's the theorem. Let Bn have generating function g of x, and I'm going to say g of x has this special form. It's 1 over 1 minus x to the alpha power plus some constant, c1, it could be any constant, c1, times 1 minus alpha to the, or 1 minus x to the alpha minus 1 power, plus any constant c2 times 1 minus x to the alpha minus 2 power, all the way down until I get to some constant ck over 1 minus x to the alpha minus k power. And here I'm going to say that I want alpha minus k to still be positive. So I still want to have this division being present. So I want to say that alpha has to be bigger than k. So let's say I have this as my generating function. So what I'm saying here is this g of x can be expressed as the sum bn x to the n. And g of x can also be expressed in this form. So the first result is, in this situation, Bn is asymptotic to n to the alpha minus 1 power divided by gamma of alpha. So what I'm saying is, if you happen to find a generating function and it looks like this, you can immediately get the asymptotics of the coefficients in this way. So let's show why this works. I can use Newton's binomial theorem. Each one of these I could expand and write g of x as the sum, n going from 0 to infinity, of negative alpha, choose n, plus a constant c1 times negative alpha plus 1, choose n, and I can keep writing down the constants until I get to ck, negative alpha minus k, choose n. All of that would be times minus 1 to the n, x to the n. So thus, I can lean on the result we found in the previous video, and I can write this as the limit as n goes to infinity of bn divided by n to the alpha minus 1 power divided by gamma alpha. Now, I'm going to write bn down. I guess when I wrote g of x using Newton's binomial theorem this way, I'm explicitly telling you what the coefficients bn are. So let me copy that down. That's the limit as n goes to infinity. I think I have negative 1 to the n, negative alpha choose n, plus c1, negative 1 to the n, negative alpha minus 1 choose n, and I keep going until I get to the last term. In the previous video, we saw that this bottom part was asymptotic to negative 1 to the n, negative alpha, choose n. So this first term in the limit clearly equals 1. And then in the previous video, we showed that when you divide all the remaining terms by this, you get limit 0. That was the corollary we ended the previous video with. So all those other terms, 0. I'm done with the theorem, because the definition of this asymptotic relationship is that the limit of the fraction, the ratio, is equal to 1. So there, that's the proof of the theorem. I'd like to use this theorem in generating functions I find in the wild, so I'm going to rewrite this a little bit in a little bit more general of a manner as a corollary. So here's a corollary, just broadening the class of functions I'm able to use this theorem on. I'm going to say, now suppose Bn has generating function given of the form g of x. Now I'm going to say I could have a constant here other than 1. And furthermore, I could change this 1 here to an r. So my new function is just slightly more general than my old function. It's going to look like this. I'm going to replace the ones in these denominators all with r and add things up. So I get ck over r minus x to the alpha minus k power. Again, I'm assuming that alpha minus k is still positive, so alpha has to be bigger than k. Okay, then the result is, under this condition, that Bn is asymptotic to c over r to the n power plus alpha times n to the alpha minus 1 over gamma of alpha. So here is the proof of this result. I'm going to consider the function r over alpha over c times g of rx. So I'm going to plug in rx wherever I see an x here, and I'm going to multiply the whole result by r to the alpha power divided by c. So if you do that, I believe you will get r to the alpha over c times c, and then in this bottom here I get r minus rx to the alpha. And I'm not going to write all the terms down, but you get similar terms that look like this. Then when you simplify a tad, you can cancel this r to the alpha with the r to the alpha on bottom, and you get 1 over 1 minus x to the alpha power plus these smaller terms as in the same way that we have in this theorem up here. Similarly, I can replace x here with rx in the generating function. So, and we see that r alpha over c g of rx is the sum, and going from 0 to infinity. Now, Bn has generating function g, so that means the coefficient of x to the n in g is Bn. In other words, I get r to the alpha over c Bn rx to the n power. So the coefficient in this series is r to the alpha plus n, I get an extra n here, divided by c Bn, and that should be asymptotic to the coefficient of x to the n in this larger expression, which we can get from the previous theorem. So that is equal to n to the alpha minus 1 over gamma alpha. So you could take this result and just divide by the term in front, and you achieve the corollary. All right, so these are some first asymptotic results. They're very indicative of our main theorem, which is coming up very soon. All right, I'll see you in future videos.